At 1420-2458 MHz, Brian Cox traced the hydrogen line at Jodrell Bank on 12 June 1963, letting its patient pulse steady the dusk. The dented shellac spool marked possible structured drift, in blue pencil breathed a faint, comforting static. If this quiet chronicle soothes you, please subscribe. If this starlit history soothes you, please subscribe. If this starlit history soothes you, please subscribe. Brian eased the reel onto the playback arbor as the lamp's brass chain clicked softly, his fingertips tracing the scored metal where earlier astronomers had tightened bolts with cold patience, and the acetate smelled faintly of peppered ozone released after decades of sleep. He folded his winter coat over the chair, the fabric brushing against a stack of logbooks whose leather spines had darkened with graphite dust, and he listened for the gentle thud of the motor achieving 8 inches per second. On the desk lay a velvet pouch containing the micrometer he still uses on the Large Hadron Collider, its knurled grip glinting like a pocket lighthouse as he measured tape thickness to ensure fidelity, because the story of extraterrestrial searching depends on intact grooves and trust in instrumentation. Outside the stone walls, Cheshire fog muffled the motorway hum, isolating the observatory so that his breathing became part of the room's rhythm, aligning modern curiosity with the quiet rituals of technicians who once calibrated cathode ray oscilloscopes by lamplight. Handling archives is his chosen craft tonight, giving the cosmologist tactile leverage over myths that refuse to stay theoretical, and stirring the ancient question of whether the patterns caught on this tape prove we are not alone. In the winter of '69, Galileo Galilei angled his handmade telescope toward the moon from a Venetian balcony that smelled of sea salt and olive smoke, measuring its ridges with a wooden ruler engraved in breccia, and drawing crater shadows with charcoal that stained his thumbs. The lenses he ground with horse-powered polishing wheels widened faint reflections into tangible mountains, contradicting the medieval legend that Luna's face was flawless marble inhabited by translucent angels, and instead revealing a landscape as scarred as the Apennines. He recorded terminator angles of 35 degrees, converting them into peak heights of nearly 4,000 meters, a discovery that lent weight to the notion of another rugged world where life, as speculated by Bruno, might take root. The soft creak of the balcony railing followed his every adjustment, proving how even domestic materials can escort cosmic revelations. That same night he scribbled notes about Jupiter's wandering stars, their rhythmic dance echoing the cadences once attributed to divine messengers. What mattered was the discipline of measuring light against myth, because each arc minute he calculated fortified a new kind of power, the authority of observation over hearsay, yet it also invited the lingering wonder of whether distant ridges carried their own watchful eyes. A year later in Prague, Johannes Kepler wrote his dreamlike Somnium beside a frost-fobbed window, the glass clinking softly as he rubbed warmth into the pane to see red rooftops, while an iron brazier perfumed the study with cloves he saved for sleepless calculations. He pored over lunar tables derived from Galileo, converting orbital ratios into imagined winds that might carry lunar sailors across basalt seas, grounding his fiction in meticulously computed ephemerides that supported Tycho Brahe's raw data. The manuscript, inked with oak galls, married numerical precision to the Icelandic tales his mother told about spirits riding comets, and in that union he forged a bridge between folklore and proto-science that later generations of alien seekers would cross in their own measured way. Each scratch of quill on parchment resembled distant radio static, hinting at a lineage of evidence awaiting instruments we now consider routine. He safeguarded the pages in a cedar chest, understanding that imaginative rigor could embolden future observers to keep listening for echoes near 1420 MHz. The coals dimmed. Paper cooled. The universe pressed close, unspoken, like a held breath awaiting translation. Yet Kepler's bridge trembled when the Württemberg inquisitors arrested his mother in 1605, hauling her through torchlit corridors that smelled of damp straw, because whispered accusations insisted her comet tales were witchcraft rather than speculative astronomy. The same calculations that guided imperial calendars could not shield family knowledge from suspicion, and Kepler spent months producing methodical legal defenses, stacking eyewitness testimony in parchment piles as neatly as planetary tables. Candle wax dripped over his margins while he argued that celestial pluralism was a matter of geometry, not heresy, but fear of contagion. Silenced many supporters who might have spoken on his behalf. That suppression froze the conversation about inhabited worlds across German courts, proving how fragile evidence becomes when awe unsettles authority. Brian Cox later called the episode a cautionary alignment, because the hydrogen frequency's promise depends on scholars who feel safe enough to report anomalies without risking ions. The clank of manacles echoed longer than the pace of Kepler's pen, reminding listeners that curiosity sometimes waits in enforced quiet until kinder minds rediscover it anew. By 1698, Christian Huygens unrolled his linen maps of Saturn at The Hague, their pigments smelling of linseed and crushed lapis, and resumed the conversation that persecution had chilled, writing Cosmotheris beneath the patient glow of whale oil lamps. His telescopes, calibrated with pendulum-regulated clocks he had perfected, revealed Titan's faint light, persuading him that seas and clouds elsewhere must exist, even if the shapes remained blurred. He described alien artisans forging instruments under pale suns, a vision he justified through proportional reasoning and the principle of plenitude, thereby restoring the idea that life's mathematics could repeat across the cosmos. The scratching of quill against the thick Dutch paper mirrored the kind of data logging a radio astronomer performs when noting signal-to-noise ratios near 1420 MHz, translating faint impressions into durable claims. Readers tucked the book beside navigation manuals, letting its orderly speculations seep into maritime academies that prized charts over miracles, and gradually the silence imposed by courts loosened. What mattered to Huygens was the value of disciplined imagination. It gave society permission to imagine correspondence in the sky, and kept artisans refining optics so later generations could listen harder. When William and Caroline Herschel swept the night of 13 March 1781 from their workshop in Bath, the cold smelled of cut pine from the polished telescope tube, and the metallic rasp of a file accompanied each adjustment to the 40-foot reflector that spotted Uranus. The musicians turned. Astronomers measured the planet's disk at 3.6 arcseconds through a new eyepiece they had ground with abrasive rouge, and the discovery earned royal stipends that bought more mirrors and time. By mapping nebulae with methodical sweeps, they fostered the idea that the universe was not a closed dome, but a garden of suns with potential habitats, and their quiet labour provided artisans with employment under the king's patronage, proving how precision craft could transform whimsical sky stories into national pride. Caroline's small hands, reddened from cold copper, recorded each sweep in neat columns, a domestic rhythm that resonates with the repetitive calibration of radio dishes centuries later. The Herschel's findings moved the myth of wandering spirits into the realm of catalogued realities, supporting the notion that if such surprises exist nearby, mindful listeners might hear strangers further away. Still, the appetite for marvels invited misdirection in 1835, when the New York Sun's presses clattered through humid nights, the air thick with steam and ink as reporters published the Great Moon Hoax, describing bat-winged selenites basking in sapphire forests, allegedly observed by Herschel's telescope. Typesetters set 632,000 impressions over 6 days, the lead type warming under their fingers, and the phony engravings fluttered in gaslit parlours, persuading readers that authoritative-sounding jargon could mimic legitimate measurement. The episode mattered because it revealed how public desire for alien contact could be monetized, shaping journalism's power and forcing scientists to clarify methods in greater detail. Although the story drew on existing respect for lunar cartography, the eventual debunking recentered credibility on people who could demonstrate exact instruments and logs, reaffirming that the hydrogen line of trust depends on transparent craftsmanship. Brian Cox often cites this hoax when he lectures under planetarium domes, his voice softened by the low roar of projectors, reminding audiences that evidence must withstand hand-stained presses as well as stand hand-stained presses as well as starshine. In 1877, Giovanni Schiaparelli settled into Milan's Brera Observatory as the summer heat trembled over tiles. The observatory's brass fittings warmed to the touch, and he traced Mars through an 8.6-inch refractor, while the opposition painted the planet bright as embers. He sketched networks he called canali, measuring each linear feature with angular precision, some stretching hundreds of kilometers in his careful notes, and the term simply meant channels. Yet translation carried the word across the Atlantic as evidence of engineered canals. The graphite smell of his pencils mingled with candle wax while he recorded coordinates, giving engineers and dreamers alike a scaffold to ponder Martian hydrology as a purposeful craft that could sustain civilizations. When he published the maps, the ripples reached irrigation planners and colonial strategists, showing how extraterrestrial speculation could influence earthly infrastructure budgets. The observatory fell quiet after midnight, and his assistants held their breath to steady the scope. Silence held a brief refrain. The dome creaked. Shadows cooled. The dust beyond the glass felt attentive, waiting for whatever signal might descend. Percival Lowell took Schiaparelli's charts to heart, erecting a private observatory in Flagstaff by 1894, where high-altitude air tasted of pine resin, and the newly planed wooden floors echoed beneath his boots. He invested family capital into 24-inch refractors imported from Boston, aligning them with bubble levels while telegraph wires crackled in the distance, determined to prove that Martian canal builders existed. His staff kept meticulous thermometric logs, noting nighttime drops to near freezing, and they rationed lamp oil so the dome stayed dark for sensitive plates that recorded faint albedo variations. The endeavor mattered because it demonstrated how personal wealth could harness engineering, glassmaking, and even hospitality work for a scientific narrative that promised cosmic neighbors, effectively converting myth into payroll for dozens of specialists. Yet the thin, shimmering air often introduced optical illusions, leading to sketches that later observers could not replicate, suggesting that human desire can engrave lines on the retina as forcefully as actual topography. Meanwhile, in 1901, Nikola Tesla sat within the red glow of his Colorado Springs laboratory, the ozone tang of high voltage clinging to every copper coil as he tuned receivers to 1420 kHz and beyond, reporting rhythmic pulses he believed might be extraterrestrial. He recorded the series of beeps in leather-bound notebooks, comparing them to atmospheric data, and he speculated that Mars might be signaling, which prompted him to suggest building a gigantic transmitter atop Pikes Peak. Although the pulses were likely terrestrial, his announcement stirred engineers and philanthropists, illustrating how claims of alien contact could accelerate investment in wireless communication, a technology whose cables, transformers, and operators reshaped economies. The laboratory floor vibrated under the Tesla coil's thunder, and the inventor, eyes bright behind wire spectacles, felt the thrill of bridging myth with measurable electricity. His enthusiasm seeded later research despite skepticism, teaching future seekers that even mistaken interpretations can leave behind valuable circuits and meticulous logging practices. Yet by 1909, Eugene Antoniadi stood at the eyepiece of the 33-inch Meudon refractor outside Paris, the autumn wind carrying scents of wet leaves through the open slit, and he resolved Mars with unprecedented clarity, finding that the supposed canals dissolved into blotched terrains. He sketched the planet with sable brushes dipped in diluted ink, translating red deserts into grey gradients that left no room for geometric waterways, and his published plates dampened the canal narrative that had animated Lowell's observatory. Observatory staff, aware of the uproar, maintained a respectful hush as the results circulated, proving that disciplined skepticism could halt an enthralling story when evidence demanded caution. This formal demystification temporarily quieted funding for Mars-obsessed projects, yet it also freed resources for spectroscopy and atmospheric studies, redirecting the search toward chemical clues rather than cartographic fantasies. Rain tapped softly on the slate roof that evening, a natural percussion underscoring how discovery sometimes yields to thoughtful silence for the sake of truth. 14 years later, in August 1924, the United States Navy orchestrated a national radio silence day during a favorable Mars opposition, lacing the airwaves with deliberate quiet so that officers at the Naval Research Laboratory in Washington could tune vacuum tube receivers toward 1420 MHz and adjacent bands. The control room smelled of hot dust and varnish as Chief Scientist Albert Hoyt Taylor monitored the dials beneath bluish lamps, while a rainstorm hissed against the windows, and telegraphists across the continent paused routine traffic for 5-minute intervals. Nothing definitive emerged, yet the exercise mobilized 1,500 operators, demonstrating how a collective hush could serve both national security and scientific listening, granting radio technicians a sense of participating in a planetary vigil. Local newspapers praised the discipline, suggesting that citizens' willingness to restrain chatter proved readiness to welcome interplanetary contact responsibly. In that orchestrated quiet, alien inquiry became a civic ritual, binding communities through shared obedience to silence. Still, when Orson Welles broadcast War of the Worlds in 1938, the CBS studio exhaled the warm scent of glowing tubes, and Foley artists splashed water in basins to mimic Martian cylinders hissing open, blurring fiction with reportage. The panic, though later exaggerated, revealed how fragile public trust remained, compelling astronomers and educators to clarify their messaging with calmer cadences and transparent sources. Brian Cox, decades later, would replay archival acetates of the drama, noting the precise modulation that convinced listeners they were hearing authenticated bulletins, a lesson about the responsibility carried by voices that interpret the cosmos. Radio station secretaries received flooded phone lines, their fingertips smudged with carbon paper as they noted callers' fears, and authorities recognized the necessity of pairing alien narratives with measured explanations to prevent societal disruption. The broadcast's echo became a case study in communication ethics, underscoring that the power to describe extraterrestrials carries the parallel duty to soothe. The hallway dimmed. Scripts rustled. The transmitter thrummed, awaiting calmer tales that would settle trembling listeners. During the closing months of World War II, radar technicians at Fort Monmouth repurposed their SCR-271 antennae, the cold steel smelling of machine oil, and in January 1946 they launched Project Diana to bounce 111.5 MHz pulses off the moon, listening through headphones that pressed aching grooves into their temples. The returning echo, delayed by 2.5 seconds, confirmed that radio waves could reach beyond Earth, a revelation that gave Allied communications officers confidence to pursue deep space radar and, eventually, extraterrestrial messaging schemes. Snowflakes lashed the Jersey shoreline while soldering iron smoked in the operations hut, and the disciplined timing tables they produced became templates for future SETI synchronization. The experiment mattered because it shifted alien contact from speculation to engineering. By proving the moon could reflect human signals, the team laid foundation for proactive transmissions, even as wartime secrecy temporarily hid the results from broader audiences. The generators droned steadily, suggesting that persistence and patience could make the sky audible. In the summer of 1950, physicist Enrico Fermi walked across the Los Alamos cafeteria, the air scented with chilies and machine lubricant, and famously asked colleagues, "Where is everybody?" after debating UFO reports and galactic colonization timescales. His napkin doodles calculated that even modest star-faring civilizations could traverse the Milky Way in tens of millions of years, a blink compared to cosmic age, and this paradox reframed alien talk into a problem of probabilities rather than anecdotes. The question rippled through classified corridors, aligning military scientists and academic theorists in a shared puzzle that elevated the value of statistical reasoning. Brian Cox later revisited the cafeteria, listening to the hum of refrigeration fans while filming, and he traced Fermi's insight to the modern need for patience when scanning hydrogen frequencies. Absence of evidence can be data. The cafeteria's fluorescent lights flickered softly, illuminating the uneaten dessert Fermi left behind, a quiet emblem of curiosity interrupting routine. 9 years later, Giuseppe Cocconi and Philip Morrison published their seminal Nature paper from Cornell, the campus smelling of fallen leaves and the chalk dust that clung to their tweed sleeves, proposing that 1420 MHz, our hydrogen line, was the universal hailing frequency for any civilization wanting to announce itself. They reasoned that hydrogen's spectral signature was so fundamental that physics alone would advertise the channel, and they calculated beam widths, radiated power, and receiver sensitivity required to detect interstellar messages. Their article mattered because it offered SETI a rigorous blueprint, convincing funding boards and amateur clubs alike that listening could be systematic rather than speculative. The mimeographed reprints they mailed carried the faint scent of toner, and colleagues unfolded them beside coffees that steamed in the autumn chill, feeling the thrill of a precise roadmap that linked theoretical astrophysics with practical antenna design. In that moment, the search gained legitimacy, tying academic prestige to the humble act of patient listening. Frank Drake set up Project Ozma at Green Bank in spring 1960, the West Virginia hills damp with dew and jasmine, while the 26-meter dish rotated with a deep groan, targeting Tau Ceti and Epsilon Eridani. He tuned the receiver to a 2.3 kHz bandwidth around 1424.25 MHz, calibrating against a noise diode whose warm resistor smelled faintly of singed varnish, and recorded results on reel-to-reel tapes that hissed softly. The operation required technicians to oil motors, electricians to monitor power fluctuations, and students to swat mosquitoes while logging signal strength, transforming the alien hunt into collaborative labor that trained a generation of radio astronomers. Although nothing definitive surfaced, Drake's meticulous notation of false alarms set standards for RFI mitigation, provoking reflective questions about how we interpret anomalies without leaping to myth. The gentle clicking of relays became the lullaby of science, proving that discipline and patience are themselves forms of cosmic conversation. In 1967, graduate student Jocelyn Bell, fingers numbed by the cold Armagh wind, walked the 4.5-acre Mullard Radio Astronomy Observatory, checking the 120 miles of coaxial cable that smelled of tar and wet grass, and she noticed a curious lark-like beat in the pen chart recorder. The pulse is repeated every 1.337 seconds, neatly incising ink on the paper drum beneath fluorescent workshop lights, and she labelled the phenomenon LGM1. Little green men, half in jest, half in acknowledgement that disciplined observation must consider every possibility before elimination. Her supervisor Anthony Hewish insisted on exhaustive tests, and together they ruled out radar, satellites and terrestrial interference, ultimately identifying the source as a rapidly spinning neutron star. The discovery mattered because it demonstrated that anomalies, when respected rather than dismissed, can reveal brand new astrophysical objects, equipping listeners with humility about what alien signatures might mimic. The shed smelled of solder and damp wool as Bell carefully folded the chart, knowing that skepticism paired with wonder can redraw the heavens. The sky slowed. Pens rested. The deep ticking lingered, cushioning thought for another night of listening. On 16 November 1974, the Arecibo Observatory in Puerto Rico pivoted its 305-meter dish beneath a humid twilight buzzing with coqui frogs, and engineers transmitted a 1,679-bit message toward the globular cluster, M13 at 2,380 MHz, encoding a pictogram of hydrogen, carbon, and human silhouettes. The control room smelled of warm aluminum and tropical rain as operator Donald Campbell monitored klystron power levels, ensuring the 1,000 kilowatt beam held steady, while Frank Drake stood nearby with folded arms, absorbing the significance of humanity's first deliberate interstellar postcard. The gesture galvanized mathematicians, artists, and linguists, each debating how to compress identity into binary pulses, and it showcased the value of interdisciplinary craft. Carpenters maintained the suspended platform, botanists studied rainforest microclimates protecting the facility, and radio engineers honed modulators for clarity. Though the cluster lies 25,000 light-years away, the mere act of transmission transformed global culture, inspiring textbooks and even children's games, and reminding us that the search for aliens is as much about articulating ourselves as it is about hearing others. 3 years later, on 15 August 1977, volunteer Jerry Eman circled "Wow" in red felt tip on a printout from Ohio State's Big Ear radio telescope, notes smelling of toner and grilled corn drifting from the nearby state fair, because a 72-second burst at 1425.556 MHz rose 22 times above background. The alphanumeric sequence 6EQUJ5 captured a hydrogen line strength event that matched precisely the frequency Brian Cox would one day handle on that Jodrell bank tape, and the data proved how a single column of numbers could ignite decades of inquiry. The observatory stood quiet except for cricket song and fan hum, and Eamon resisted the urge to declare discovery, instead cataloguing antenna coordinates for future cross-checks. The WOW signal's strength lay in its mystery, prompting resources for improved receivers, computing algorithms, and global collaboration, thereby expanding the workforce dedicated to monitoring the cosmic commons. To this day, the faint scent of mimeograph ink on that sheet reminds archivists that vigilance can be electrifying even when confirmation never arrives. In 1988 Manchester, teenage Brian Cox balanced rehearsal with the pop band Dare and late-night physics revisions, the studio fogged with cigarette haze and the warm plastic smell of synthesizer keys under neon lights, while he played chords inspired by cosmic chord progressions he had read about in Carl Sagan books. Between sets, he unfolded astronomical journals describing the Voyager Golden Record and fresh interpretations of the WOW signal, letting the glossy pages cool the sweat on his wrists, and he imagined that music could be a bridge for alien communication. The dual life mattered because it seeded his later talent for translating complex cosmic evidence into gentle narratives, integrating artistic empathy with mathematical rigor. The band's amplifiers hummed at 60 Hz, subliminally echoing the frequencies he would later discuss on television, and his notebooks combined song lyrics with equations about exoplanetary atmospheres. This period of synthesis gave the future professor an embodied understanding that communicating science requires rhythm, patience, and tactile detail. In 1990, NASA reoriented Voyager 1 to capture the pale blue dot, and engineers at the Jet Propulsion Laboratory watched the monitors glow turquoise in a control room perfumed with brewed coffee and heated circuitry. The image, 0.12 pixels wide, drifted through data links that crackled softly, and Carl Sagan's team interpreted the delicate beam of sunlight streaking across Earth's minuscule silhouette as a humbling reminder of home. The photograph influenced international policy discussions, environmental activism, and even Brian Cox's later BBC scripts, all emphasizing that if aliens exist, their perspective on our spec would demand stewardship as a prerequisite for conversation. Technicians wearing headsets kept fingers poised above keyboard toggles, ensuring the deep space network maintained alignment, a ritual of attention proving that distant signals depend on terrestrial artisanship. The pale dots solidified the emotional core of alien thinking. Before we greet others, we must attune to our own fragile glow. In 1995, Michel Mayor and Didier Queloz measured the star 51 Pegasi from the Haute-Provence Observatory, the night air aromatic with lavender and machine grease, and they tracked a velocity wobble of 59 meters per second using an Echelle spectrograph chilled to stabilize its components. The absorption line shifted with clockwork regularity every 423 days, revealing the first confirmed exoplanet orbiting a sun-like star, a gas giant hugging its parent in a searing close embrace. Their meticulous temperature control, data logging, and statistical analysis proved that other worlds could be detected without direct imaging, empowering dedicated instrument builders and forging new careers in precision photonics. The discovery reframed alien discussion from speculation to demographics, strengthening arguments for habitability studies and eventually fueling missions like Kepler. Mayer's pencil etched light curves in a leather notebook, while Queloz's wool sweater carried the scent of midnight dew, grounding revolutionary insight in everyday textures. The shutters sighed. Monitors dimmed. Lavender drifted, draping the room in patient expectation for whatever sky secret came next. In August 1996, NASA scientists gathered at Johnson Space Center, where the sterile corridors smelled of disinfectant and chilled metal, unveiling electron microscope images of the Martian meteorite, ALH8401, that displayed carbonate globules and worm-like microstructures, a fraction of a micron long. President Clinton's televised remarks carried the excitement into living rooms, while laboratory technicians calibrated mass spectrometers to analyze isotopic ratios of carbon and oxygen, searching for biosignatures that might betray ancient Martian microbes. Although subsequent studies suggested inorganic processes could sculpt similar shapes, the announcement galvanized astrobiology funding, justifying cleanroom expansions, Antarctic meteorite expeditions, and microbial extremophile research. The polished slab of the meteorite felt cold and granular in gloved hands, linking Antarctica's ice fields with Martian deserts and the possibility that alien traces might already be nestled inside Earth's rocks. The debate underscored how ambiguous evidence can still nurture disciplines, providing employment and intellectual momentum even when conclusions remain tentative. When the Cassini spacecraft in 2005 skimmed past Enceladus, onboard instruments tasted salt-rich plumes spraying from fractures dubbed tiger stripes, while mission control in Pasadena hummed with printer chatter and the scent of coffee beans roasted nearby. The cosmic dust analyzer detected sodium salts and microscopic ice grains, and the ion and neutral mass spectrometer registered organic molecules, suggesting a subsurface ocean interacting with a rocky core. These measurements empowered planetary geologists, chemists, and cryovolcanism experts, creating new research fellowships and directing attention to moons as prime candidates in the alien search. Engineers meticulously monitored reaction wheels and hydrazine levels to ensure future flybys, revealing how every actuator and gasket contributes to the grand narrative of seeking life beyond Earth. The faint blue glow of console screens washed over faces as the plume data scrolled, and a murmur of awe settled like frost, emphasizing that even cold geysers can warm imaginations. In March 2009, the Kepler spacecraft launched atop a Delta II rocket, its fairings smelling of hydraulic fluid and insulation, and once settled into solar orbit, the photometer stared at Cygnus, measuring stellar brightness changes with 30-minute cadence. The silicon detectors operated at 85 degrees C, their dark current carefully subtracted, and the mission soon produced thousands of transit curves showing planets of every composition, establishing that worlds are abundant and statistically inevitable. Data analysts huddled in windowless rooms illuminated by dual monitors, sipping herbal tea while cross-correlating faint dips only 84 parts per million deep, and their collective labor converted the intangible dream of extraterrestrial neighbors into a catalogue of coordinates. Kepler's stability depended on reaction wheels lubricated with sputtered molybdenum disulfide, a reminder that the search's success rests upon materials, science as much as cosmic curiosity. Each confirmed planet broadened imagination's horizon, urging society to prepare linguistically, philosophically, and ethically for eventual contact. In 2015, under the vaulted ceiling of London's Royal Society, the air perfumed with polished wood and old paper, Stephen Hawking and Yuri Milner announced breakthrough. Listen with Brian Cox seated nearby, his hands resting on the cool armrests as cameras clicked like faint rain. The initiative committed $100 million to upgrade radio telescopes at Green Bank and Parkes, installing digital backends capable of processing billions of channels across the 1 to 15 GHz range, with special attention to the 1420 MHz beacon. Software developers compiled code in labs that smelled of solder flux, while data archivists arranged petabytes of storage cooled by hissing ventilation, employing hundreds of analysts who combed for narrowband carriers. The announcement reinvigorated global cooperation, offering students paid positions to learn signal processing, and it tethered the motif of disciplined listening to tangible resources. Cox later described how the room's quiet after Hawking's speech felt like velvet, a collective silence charged with hopeful responsibility. In October 2017, astronomers at Haleakala's Pan-STARRS facility smelled volcanic earth cooling at dusk as they discovered the interstellar object, One-Eye Oumuamua, streaking away on a hyperbolic trajectory, its brightness curve suggesting a tumbling, cigar-shaped shard only a few hundred meters long. Spectrographs showed no cometary coma, and its acceleration puzzled researchers, prompting debates ranging from hydrogen ice sublimation to light sail speculation. The observation mobilized observatories worldwide, proving that the alien question now includes artifacts and debris, and it encouraged policymakers to fund rapid response telescopes capable of tracing such visitors. Brian Cox discussed the findings on air from a BBC studio lit by gentle LEDs, explaining with soft cadence how extraordinary yet natural physics could be, and how our readiness to interpret anomalies defines the narrative's credibility. The summit winds hushed as telescopes tracked the faint traveller. Shadows stretched. Instruments cooled. A whispered awe hovered between each calculation offered, holding scientists in gentle, questioning stillness. In 2020, the Canadian Hydrogen Intensity Mapping Experiment, CHIME, in British Columbia captured the first fast radio burst repeating on a precise 1635-day cycle, the cryogenic receivers exhaling vaporous plumes into the frigid dawn air tinged with pine sap. Technicians in insulated gloves adjusted digital beamformers, listening to the low whir of cooling pumps while the data pipeline flagged the periodicity, and the discovery suggested that magnetars or binary interactions might mimic or mask engineered signals. The result mattered because it forced SETI analysts to refine filters, distinguishing natural astrophysical rhythms from potential intentional beacons, and it spurred collaborations with gravitational wave observatories to watch for correlated events. Brian Cox recorded a segment describing the finding on a remote microphone wrapped in felt to reduce crackle, his voice threading excitement with calm, reinforcing that each mysterious pattern teaches us how to interpret the hydrogen channel with greater nuance. By 2022, the James Webb Space Telescope deployed from L2, its sunshield unfurling with the faint crinkle of Captain remembered in ground tests, and its instruments sniffed the infrared spectra of exoplanets like WASP 96b, discerning water signatures within atmospheric mists. In mission control at Goddard, engineers monitored cryostat temperatures bathed in soft amber status lights, and they shared chocolate bars to steady nerves as the mid-infrared instrument settled at 6.7 Kelvin. The resulting absorption lines offered tools to probe for methane disequilibrium, a key biosignature, and they validated decades of mirror polishing labor by technicians whose fingerprints never touched the pristine gold. The reverent hush that followed first light was silence born of awe rather than fear, yet it motivated astronomers to keep calibrating, to improve pipeline subtraction, and to dream of detecting even faint chlorophyll red edges someday. Through Webb's vision, the alien question gained textures of vapor and light, not merely numbers. Tonight, as Brian Cox steps across the red soil of Western Australia where the square-kilometre array's first dishes await activation, the desert air tastes of iron dust and eucalyptus, and the Milky Way arches like a silvered river pouring silence into his cupped hands. He listens to technicians discussing fibre-optic timing lasers that pulse green through corrugated conduits, and he feels the vibration of cooling fans through the soles of his boots, reminders that each bolt and waveform is a pledge to the hydrogen whisper first traced on that Jodrell bank reel. Memories of Galileo's charcoal, Kepler's cedar chest, Huygens's whale lamps, Lowell's pine-scented dome, Bell's inked charts, and Voyager's pale pixel settling on a cobalt screen all converge in his breathing, suggesting that every generation's discovery, suppression, and rediscovery flows into this desert hush. The dishes gleam under starlight, their mesh cold as river stones, and distant dingoes call with a soft yip that feels like punctuation to an unfinished sentence. He wonders, not aloud, but in the steady rhythm of his pulse. Whether the next faint carrier, once sifted from cosmic noise, will sound like a chord already written in his youthful synthesizer, or like a completely new timbre waiting to be named. The night does not answer. It only holds the question open. Wide is the frequency that drifts between worlds.